In this tutorial, we will be discussing balancing chemical reactions. Okay, so we represent chemical reactions with chemical equations. The substances on the left are the reactants, and the substances on the right are the products. We often specify the state, physical state, solid, liquid, or gas, of each reactant and product with parentheses next to the formula. So here's an example. We have methane, which is CH4. It's reacting with oxygen, O2, to form carbon dioxide and water. So here we have the starting stuff, which is the reactants, forming the products, which is what we have at the end, and an arrow between them. The arrow often you'll see written decays, or it could say to form, to produce. Anything along those lines where you're changing one thing to another, that is what's meant by the arrow. So notice also here we have this G here. This G in parentheses means gas. So this is the physical state of each of the substances. If, for instance, this water was in a form of a liquid, it would have an L next to it instead. One that people aren't used to seeing is AQ, which is aqueous. That just simply means it's been dissolved in water. So let's look at what these chemical formulas actually and chemical equations actually mean as far as what's happening. So here we have CH4. Here we have O2, CO2, and H2O. You can see that each of these numbers represents an atom. So the atoms at the beginning have to be the same as the atoms at the end. That follows the law of conservation of mass, or the law of conservation of matter. Both generally say the same thing, that the left has to equal the right. Kind of like a mathematical equation with an equal sign between them. The left has to equal the right. Atoms don't just disappear, they don't just appear, they come from somewhere. And that's what we're trying to show here. So for instance, here we have 4 hydrogen atoms. And on the right hand side, we have 2 hydrogen atoms. Those have to be equivalent. So that means I have to figure out how to get 2 more hydrogen atoms on the right hand side. We do this by adding a coefficient in front. So that way we're saying we have 2 of these molecules. So if I put a 2 here, that means I'm having 2 molecules, 2 water molecules. So that means we have a total of 4 hydrogen atoms over here now. 2 times 2, because there's 2 sets. We cannot just randomly put numbers in here. Once those subscripts are there, they have to remain there. They cannot change. What you can do is change the quantity of molecules. So here I have 2 H2O, meaning I have 2 water molecules. These numbers didn't change. They're both the same molecule, same type of molecule. I had to do the same thing with the oxygen over here. We have 2 oxygens. Now we have 2 oxygens over here because 2 times 1. So I have a total, when I add them together, of 4 oxygens. Because of that, I can multiply the oxygen here by 2, saying I have 2 sets of oxygen molecules. This is now called a balanced equation, because the left hand side has the same number of atoms on the right hand side, and it's balanced out. So if we check for the balanced equation, we can say that there's 1 CH4 molecule, 2 O2 molecules, 1 CO2 molecule, and 2 H2O molecules. If there's no coefficient, there's a 1 there that they just don't write. So here we have 1 times 1, which means that we have 1 carbon. 1 times 4, which means we have 4 hydrogens. 2 times 2, which means 4 oxygens. On the right hand side, we have 1 times 1 carbon, 1 times 2, which is 2 oxygens. However, we have 2 over here as well with a plus sign between them. That gives us 4. And then we have 2 times 2, which makes 4 hydrogens. The left side and the right side are the same. A balanced chemical equation represents a chemical reaction. In this image, the methane that we were just referring to is being burned in oxygen to form carbon dioxide and water. That's what's happening with this stove. Alright, so let's do some more of these practice problems. What I typically do is I put the elements that I'm trying to balance, not the molecules, the elements. So O2, that has one element of oxygen. We have 2 on the left, and we have 3 on the right. I need those numbers to be equal. So I think to myself, what is divisible? What's the smallest number I know that's divisible by both 2 and 3? The answer is 6. So what times 2 is going to equal 6? 3 times 2 is 6. I can do the same thing on the right hand side. 2 times 3 is 6. So now I have 6 on the left and 6 on the right, and it's now balanced. Once again, write out all your elements. We have Na, H, and O. We have 1 Na on the left, 1 Na on the right. 2 Na on the left. We have 2 here, but we also have 1 here with a plus sign between them. So 1 plus 2, I have 3 on the right. I have 1 on the left for oxygen and 1 on the right for oxygen. The only numbers that aren't the same here are hydrogen, so we need to fix that. If I put any number in front of the water, it's going to have to be an even number because something times 2 is going to be an even number. If I do that over here, this is odd. I have to figure out how to make that an even number to make it balance. So if I look here, there's an invisible 1 here, and there's 2. I can multiply this by 2, giving that an even number. So now we have 2 times 1, which is 2, plus 2 more is 4. That also messed up my other stuff though. So now I have an extra sodium to give me 2 sodiums, and an extra oxygen to give me 2 oxygens. So I have to balance that off on the left hand side. So sodium, I have 2 on the right, so I need to multiply this by 2 on the left. That gives me 2 sodiums. I have 4 hydrogens, and I have 2 on the left. Multiply that by 2, and that gives me 4. Now let's look how the oxygens look. 2 oxygens. On the left-hand side, I have 2 times 1 to give me 2. Now everything is balanced. I've noticed over time that when students see things written out in words, that's when they get freaked out. That's when they get scared. So what we're going to do is we're going to go through several of these and just take it one step at a time. Write a balanced equation for the reaction of solid aluminum. It's just Al. It's all by itself. With, so that means that's a plus sign, aqueous sulfuric acid. Ic came from 8, so that's sulfate. So that's sulfate is SO4. It has a -2 charge, so that means I need hydrogen here, and I need 2 of them. To form, that's my arrow. Aqueous aluminum, and sulfate. Whenever you see things written out like this, if you don't see prefixes, that means you're going to have to figure out the charges and crisscross. So aluminum is a +3, sulfate is a -2. Crisscross that down. That 2 means that there's 2 aluminums. That 3 means that there's 3 sulfates. And hydrogen gas. Hydrogen is a diatomic molecule, which means it's going to be H2. So I'm going to scribble out my charges here because I've already dealt with those. Now I'm going to write out what needs to balance. We have aluminum, hydrogen. I see sulfate on the left and on the right, so I'm going to keep that as a whole rather than breaking it up into sulfur and oxygen. You could break it up if you wanted to, but it's easier if you keep it together. So there's my sulfate. Aluminum, I have 1 on the left and I have 2 on the right. Hydrogen, I have 2 on the left and 2 on the right. And sulfate, I have 1 on the left and 3 on the right. Alright, so let's take a look at how we're going to resolve this. we have, I'm going to start at sulfate this time because that has the biggest difference here. So I have 3 sulfates on the right. I need to get 3 on the left. So I'm going to multiply this by 3. That gives me 3 times 2 hydrogens to give me 6 hydrogens. This also means that I need to change this. What times 2 is equal to 6? And that's 3. The only thing that's not balanced at this point is the aluminum. So I can put a 2 here. And that will give us our final answer of 2Al plus 3H2SO4 yields Al2SO4 3 and 3H2. Let's do another one. Sulfuric acid, ic, came from 8, so that's sulfate. Sulfate has a -2 charge, which means that I'm going to need 2 hydrogens to balance it out. Sulfuric acid is added, so I have a plus sign there, to a solution of barium acetate. Barium is Ba, acetate is C2H3O2. I do not see prefixes here, so that means I need to figure out the charges. I can look on the periodic table and see that barium is a +2. C2H3O2 acetate is a polyatomic anion, and it has a -1 charge. We can crisscross this to be BaC2H3O2 2. To form, that's my arrow, barium sulfate, BaSO4. Ba is a +2. Once again, look on the periodic table for that. SO4 is a -2. It's a polyatomic ion. They cancel each other out. They're the same. And acetic acid. So acetic came from acetate, so C2H3O2. That has a -1 charge, which means I need 1 hydrogen to balance it out. Once again, I have the polyatomic ions there. I see them on both the left and the right hand side, so I'm going to keep those as wholes because it just makes the balancing process easier. We have hydrogen, we have sulfate, we have barium, and we have acetate. Alright, so hydrogens, I have 2 on the left and 1 on the right. Sulfates, I have 1 on the left and 1 on the right. Bariums, I have 1 on the left and 1 on the right. And acetate, I have 2 here, and I have 1 on the right. So the only thing that doesn't match up is the hydrogens. So if I look here, I have 2 hydrogens on the left hand side. Over here I only have 1, so if I multiply this by 2, that means I have 2 hydrogens now. That's the only number I put in there. That's the only coefficient. So that also changed the acetate to 2. And now it's all balanced. Ammonium chloride. Ammonium is NH4. Chlorine is chloride. And H4 is a +1. That's a polyatomic cation. Chlorine, if I look on the periodic table, it's -1. Crisscross it and it's 1 and 1. You have to do that every single time you do not see prefixes. Are added, so I get the plus sign, to a solution of barium hydroxide, or sodium hydroxide. Na is sodium with a +1 charge. OH is a -1 charge, to produce ammonium with a +1. These cancel out, by the way. I didn't comment on that. Hydroxide is a -1, so that cancels each other out. And sodium and plus sodium chloride, +1, -1. And those can cancel out. Alright, so once again we have polyatomic ions on both sides. NH4, Cl, Na, OH. I have 1 ammonium on the left, 1 on the right. 1 Cl on the left, 1 Cl on the right. 1 sodium on the left, 1 sodium on the right. And 1 hydroxide on the left and 1 hydroxide on the right. So this one's already balanced, so I don't have to put any numbers here. remember, when you don't put a head number, there's automatically an invisible one written there. One thing I want to point out, now that we're starting to get the hang of actually balancing, let's put in the symbols, the physical states. Ammonium chloride crystals. Crystals are solids. So I could put a little S here if I wanted to. That does not affect the balancing. All that does is affect the physical state. It just gives you more information. Solution of sodium hydroxide, which means this would be aqueous, AQ, to produce ammonium hydroxide and sodium chloride. Since it's in a solution on the left-hand side, nothing's going to fall out of solution here, so we're going to keep it AQ. It's potential that this forms a solid, but we haven't talked about solubility laws yet. And that is how you do balancing chemical equations.